Want to do a little bit more of them because they do tend to cause problems. We're going to create a table, and it's a table made up of multiple pieces of information, and that's what tends to cause a problem. This one here is very similar to question 1. And then I want to do 2 more tree diagrams because they also cause problems. There's so much information tied up in it, and the way they're phrased sounds like a lawyer got involved. And then once we've done that, we'll then move on to still on probabilities, but that's pretty much everything that we need to worry about as far as homework's concerned, and as far as the next test is concerned. So although we'll be doing, although the next section is not for homework and it isn't necessary, it's a good idea to have if you have time to do it. So let's look at this story. I've kind of cut down all the words, but essentially there's a college, and in one quarter, let's say the quarter that we're in right now, they did a quick survey and they found out that 55% of the college are males and 45% are females. Okay. Of the males, 40% were taking a math class that quarter and 60% were not taking a math class. Of the females, 70% of them were taking a math class and 30% were not taking a math class. So you see this as like information inside other information, right? It's again a 2-tier stage. And the question goes something like this. There are 4,000 students. Complete this table. So we have to figure out how we're going to split up this 4,000 to take account of these 2 distinctly different pieces of information. So the first thing I'm going to use, you can do it all sorts of ways, but I'm going to use a little tree diagram because I'm a visual person and I like to see pictures. In this case, 55% are male and 45% are female. And what I'm now going to do is I'm going to calculate how many people that really is. Now, if there's 4,000 students and 55% are male, would you agree it's pretty easy to find out how many people that is, right? How many males that represents. So I'm just going in here and I'm doing 4,000 times 0.55 and I get 2,200. So there are 2,200 males. And if I do the same thing with the females, there are 4,000 at the college and 45% of them are females, so that is 1,800. Now what I'm going to do is, there are 2 distinct things that the males could be doing. Some of them are taking a math class and some of them are not. And the ones that are taking it is 40%, and the ones that are not taking it, obviously, are the other 60%. Now, do you notice that this 40% and this 60% are referencing the males? So it's 40% of this number and 60% of this number. Does that make sense? Why I'm taking 40% of this red number rather than the total, right? So again, it's a calculator thing. I should be able to do this in my head. So here it goes. What's that going to be for? 880. And I guess I should do the other one just to be sure. 2,200 and multiply it by 60%, and I get 1,320. So I've actually got the first 2 numbers that I can use to fill in here. For the males, taking math is 880, and not taking math is 1,320, and that does add up to what it should add up to, the 2,200 males. We happy with that one? Right, let's do the females now. We'll see how they split. According to this story, 70% of them are taking math, and then the other 30%, they're not taking the math. And so it's 70% of this number and 30% of this number. So I'm not risking my brain this time. 1,800 times 70% gets me 1,260. And 1800 times 30% gets me the other 540. And so I can now go over here, and female taking math is 1260. And those that are not taking math is 540. And that should add up, and it does, to 1800. Now I can get a total that I wouldn't have been able to find if I hadn't created this table or something similar to it. If you add up this row, aren't you getting the total number of people who took math? So can you imagine, you might get a question like, how many people at this college are taking math? Right? And you see it's made up of two distinct groups added together. So, oops, clear this out. 880 add 1260, and the answer is 20. Oh, I should do a different color just because I can. 2140. And if I add up these two guys, you get 60, you get an 1860. And now if I add these totals together, or if I add these totals together, whoops, God, I get things all over the place. Do you see that they both add up to 4,000? Does it make sense that they should add up to 4,000? And isn't that a way of checking that you've done your numbers right? So when you're creating this table, you will need to fill in these totals. And this one here is kind of helpful, because if going this way, it was 4,100, and going this way, it was 3,900, would you agree there's something wrong somewhere, right? Yeah. One of my numbers here, I hit the wrong button. I did it in my head, and perhaps I shouldn't have. We have got that. So I can then, using this guy, answer some other questions. I could also use this table. What's the probability that I choose one person at random, and it's a female who is taking math? Now we know that probability has got two numbers, right? Bottom number is who I could be talking about here, and the top number is how many ways can this happen? Right, females who are taking math. Females who are taking math, as you agree, it's 1260. Right? Top number. Bottom number, 4,000. Now, if I do that calculation as a decimal, it's going to be 1260 divided by 4,000, and the answer will be 0.315. If I wanted it as a percentage, it would be 31.5%. If I wanted it as a fraction, shouldn't I have to simplify this fraction down? I could just do it the usual by hand way. Have I shown you yet how you can use the TI-84 to simplify fractions? Very cool. Let me show you. You go 1260 divided by 4,000, just like we did, and you hit enter, and you get the usual decimal. Nothing special yet. Here's the trick. See the math button? Hit math button. Do you see option 1, FRAC? Pick that one. That means just hit enter. And what it's going to do is going to turn the answer into a fraction. There you go. 63/200. I don't know about you, but isn't that just a little bit easier than trying to do it by hand, especially if it's really ugly top and bottom numbers? Because I don't know how many times I've had to do that and just been careless and called it, I don't know, 63/20 or something, right? Lose a zero or whatever. Are we comfortable about a question then that's got two sets of information, and how this tree diagram helps you to build the table? And then from the table, you can be asked almost any permutation. Here's another one. You're picking someone at random, right? Whoops, let's put it in English first. Given that it was a math, right? Given that it's a race resistant English. There. How about you know the person is taking math? What's the probability that it's a male? So you went into you're picking one person at random who's taking math. What's the probability that it's male? Now, the bottom number is not 4,000. Isn't the bottom number how many people are taking math? And in this case, don't you need to know that total, which is 2,140? And only looking at the table that has the math people in it, can you see now that all you need to now look at is how many of those are males? And so if I went and picked a person that was taking math, the probability that that person is a male would be 0.41, at least to 2 decimal places, because the book rounds off numbers that are horrible. So far, so good. So that guy there is going to be like your template. There's I think there are only some like 6 questions in this entire piece of homework. So that's going to be your template for the make a table, answer questions kind of thing, right? The 2-tier story. An example of that would be, for instance, question 1 in the homework. Right. Now, the next guy I want to do, I think I'm going to do 2 of these guys, are going to be some more of the T-diagram ones. So this particular question that I'm going to do now is going to be very similar to question 3. Right. So, oops. I'm just moving the window back. So an airline offers a special ticket called an advance purchase. And that's for people who buy their ticket early, right? So if you do an advance purchase, that according to them is at least 4 weeks away, and you'll probably get a cheaper ticket, right? You know, if you go and you try and get a flight to Houston and you want it today, do you know you're going to pay an arm and a leg to get that ticket? Because the airlines just bump up the price. They figure out if you need to go today, it's probably important, and so they can get away with it, right? But if you buy a ticket like 3 months from now, when you're going to fly, you typically get a better price. So that's an advance purchase. I'm sure you've seen that. And what do they notice about these people? Well, so the airline notices that 40% of its customers use, can I just call it AP, advance purchase, right? And the other 60% don't use it. In other words, they just buy their ticket, 3 weeks before they go, 2 weeks, maybe even tomorrow, right? The next, yesterday, whatever. That's the first piece of information, right? That's like the 2-tier thing. Now we have a second tier. They have a thing called the no-show rate. I've never understood this, but evidently it's very common. Do you know that people buy tickets and then just don't turn up? Right? They no-show. And I thought, you spent a lot of money. You bought the bloody thing, and then you don't turn up. Now, there might be reasons you can't go. You thought you had the days off, but the boss says you can't go, whatever. But they don't turn up. And the information about who doesn't turn up is connected to these guys. So, of the people who use advance purchase, right, of those ones first, so who buy tickets, don't take advantage of this. Airline has 40% of its customers who buy tickets but don't take advantage of the advanced purchase law. The not advanced purchase people, right? The no-show rate for those who don't have advanced purchases is 45%. Wow. No-shows. And while for those who do have them, it's only 5%. Now, you might think there's something missing here. And there is. It's what percentage actually turn up for the flight. I'll call them the show-ups, right? So there's no shows, don't turn up, and then the show-ups do. Do you know if I tell you this number, isn't it obvious what the other number has to be, even although they didn't explicitly mention it? Would you agree that you either show up or you don't? So 5 of you don't show, the other 95% did show up. The not advanced purchase group, 45% did not turn up. Yikes. Doesn't that make 55% do turn up? So far, so good. So it's, as I said, it's a bit like I had to read about 4 times before I got my head around it. But it's like a 2-tier, isn't it? You have an advanced purchase or you don't. The advanced purchase people, some show up, some don't. The not advanced purchase people, some show up, some don't. That information is all given in terms of percentages. What we're now going to do is create the tree diagram from this story. There's going to be a little bit of difference, and the difference between the one I just did, which had numbers on it, right, is that this one won't have the numbers in it. It will just have on the lines what the percentages are, and then we'll show you what we can do here. So you can have advanced purchase, or you're not an advanced purchase. And the rate was 40%, which you turn into a decimal. And 60% go there. Now for the advanced purchase, there is those who are no-shows, they don't turn up. And the ones that show up. Right, for the advanced purchase people, the no-shows are only 5%, and the show-ups are the other 95. For not advanced purchase, the no-shows are ridiculously high, 45%. And for the show-ups, it's the other 55%. Now, what I'm going to put here is essentially the probability of each of these 4 combinations, because technically these are the 4 things that could happen, right? You could have a passenger that has an advanced purchase, but they don't show up, or they do. You know, there are 4 of them. And the way that you get the probabilities of these 4 events is you multiply the pathway that got you there. So let's do the top one. Advanced purchase people who don't show up. 40 and 5. So you just do multiply the 0.4, this with the other one, 0.05, and the answer you get is 0.02. And for those people who like percentages, that's only 2% of all the people who bought a ticket, right? Whether they turned up or not, only 2% of them fall into this category of advanced purchase no-shows. Now, if you do the other one, you're going to get 0.4 times 0.95, and that adds up, or that becomes 0.38. So that's 38%. Now, do you notice that this adds up to the 40%? And it should, shouldn't it, really, if you think about it? Now, how does this 60% split? Well, they split up this way as well, and we do it the same way. So 0.6 times 0.45, and that gives me 0.27, which is essentially 27%. And then, well, actually, I should be able to figure that out. If I cover this up, if these are 20% and this makes up 60% of everybody, would you agree that this should be what's left? Shouldn't this be 33%? Let me say that again. Shouldn't these two guys add up to that 60%? I already know this is 27. Shouldn't this be 33? Let's use it as a check. That you get by multiplying this guy and this guy. So 0.6 times 0.55. Am I good or am I good? I did not screw this one up because it's easy to do. Now that I have got this fella totally done, what would that look like? How would you do the answer to that in your homework? So let me just jump out and show you how the WebAssign gets you to do the answer. Do you see that they've got the essentially my tree diagram? Do you see it? I'm assuming you can see it. Are you looking at question 3 as I am? Yeah. Now, A was shooting space. I did advanced purchase at the top and not advanced purchase at the bottom. Not a big deal, right? So in my case, the no advanced purchase people would be A, and that's 60. So I'd put 0.6 here, and I'd be putting 0.4 there. Right, and do you see that guy that I'm calling P? They call PN. Who knows why they called them those letters? Let's pick U. U is an advanced purchase and a show up. And an advanced purchase and a show up is 0.38. So do you see that list is basically all the guys that I have on my tree diagram? And you know, I'll get the letters wrong, but A, B, C, D, E, F, G, H, I, J, right? That kind of lettering system. So if you create your tree diagram, each one of these numbers here corresponds to one of the letters in your homework, right? So that's how they get you to still drawing a T diagram. Now, since you've got this particular T diagram, what do they do in part B? They get you to fill in a table. And the table looks something like this. You have the shows. Oh, well, I call them show ups. I'll call them show up. And the other one, they call the no shows. And the total. And advanced purchase and not advanced purchase. And the total goes here. They said, create a hypothetical 100,000 table. What are they talking about here? Well, do you know all these percentages I've got here? Don't they correspond to one of these 4 boxes? So let's take one example. See this 2%. Isn't this advanced purchase, no show people? Right? Advanced purchase, no show, 2%. Advanced purchase, no show, 2%. But 2% of 100,000, 2,000 people. That makes sense? Right. Now, if you go through all the other groups, this ends up being 38,000. What's that? No-show. This is 27,000. And this one here is 33,000. And if I add these up, I get 40,000 and 60,000. And if I add these up, I get 71,000. And if I add these up, I get 29,000. And yep, I get 100,000.
Professor, somebody just texted
Yes,
me and said that they're in the waiting room.
I can't see them.
Are they not there?
Yeah, but thank you for telling me.
Okay.
No, they're not here. I'm not. I don't know where they are, but they're not there. But thank you. It's always good to tell me that. Are we comfortable about this table? Now, once you've got these tables, can't you get what's the probability you pick somebody at random and they are a no-show? Well, won't the no-shows be 29,000 out of 100,000? And what's that? That's 0.29, which is 29%. So according to this table and this airline, it doesn't matter how you buy a ticket, 29% of them don't turn up. I'm not sure how realistic that is. From what I know, airlines, and don't quote me on this because it might not be exactly right, but as far as I know, airlines always assume about a 10% no-show rate. And that's why just now and again, don't they get overbooked? And you think, well, how can you overbook? Well, if you don't assign seating, which you can certainly do that, couldn't you book 5% more people than the plane can hold? Because aren't you going to assume that 10% don't turn up? And you can see from the airline's point of view, can't you make more money by doing that? Just curious, has anybody been on an overbooked flight? I have. Did you get the good deal that I got?
Yes.
Yeah, do you want to share your deal and then I'll share mine, see if they're similar? What did you get?
Well, I don't know if yours, I mean, yours might have been better than mine, but I was bumped onto like a flight an hour later, was given a free ticket, and then was bumped up to first class.
Oh God, no. You got a sweet deal there. I thought I was doing good. I got $200 in the next flight. So they gave me not 200 physical dollars, but they gave me a credit on my next flight. You got a brand new ticket and a first class. Did you volunteer for it or did they kind of make you do it?
That's funny because my mom flies a lot, so whenever there's like a first class seat open, usually they give it to the person that flies a lot or like military, and that's happened to my mom before where she gets the free first class ticket.
I have only been first class once and it's so good I want to do it again, but my sister-in-law worked for Alaska Airlines and she just was saying goodbye to us and she knew the woman at the gate and they were chatting away and obviously she mentioned that me and my wife were there or something, and when we got on there must have been 2 free first class seats and she said, oh, you can just sit in these. And do you know what they give you in first? You know this, David. They give you towels like to wash your hands with, and they give you real cutlery and free drink, and the food is better. Did you get the whole thing, including the cutlery and the whole thing?
The whole thing.
Oh,
yeah.
I am so jealous.
Well, and if you're traveling internationally, your bed goes, or you have a bed, which that's.
Oh God!
that's
Don't
where
tell
it's
me it was
actually at.
it wasn't an international flight as well, David, was it?
No, not this time. I frequently get bumped up to first class. I don't know why. I have read that it's being nice to people, but I got bumped to first class from Europe back to the States, and it was pretty incredible.
Oh God! When I go to Scotland, I get the IKEA seats. Do you know the ones? Because I'm a big person, where you sit like this and you're. Oh God! I'm a sardine, and you're getting first class. The world is not fair. But I'm pleased
It's
for
on a
you.
17-hour flight to Japan, and I am 6 feet tall.
Oh God,
I,
you poor soul.
I think it was one time we got like first class tickets when I was flying with my mom and my brother. I think it's because we had like enough miles to where it was cheaper. That's the only time we flew first class, but my brother didn't want the meal that they had in first class, so he switched with someone in the economy because he wanted the economy meal. Someone gladly took it.
You know your brother isn't too bright. If you mind,
He
don't
was
mind me
like
insulting him.
6, and
Oh, okay. 6 don't know anything.
I mean,
That's
he
okay.
wanted the sandwich that they had in the economy.
Okay.
He wanted his cheese sandwich, and we were little then. That's the only time we got to fly first class, but my mom thought it was quite funny.
Yeah. So,
Did you go back with them, or did you just send a 6-year-old into the back of the plane?
No, they just asked it. The flight attendants asked if anyone wanted to switch.
oh, and after the riot stopped, they picked someone.
I don't know.
Okay, everyone, that's my fault. That was interesting. I want to just show you on the time that we've got the rest of these questions from that very small section. Very small, but quite time consuming, as you probably see. So I was originally going to do 2 of these, but just time got the better of us, so that's fine. The one I've just done is essentially question 3, right? The airline one. And you can see the table. And then they ask you questions, you know, that you can either get the information from the table or you could use a T diagram. Now, and this is basically another story of the same kind of 2-tier thing. It looks like in this case, oh no, it's not. Take that back. Okay, I'm changing my mind the minute I saw this. I superficially just thought it was another example of a 2-tier. It still is a 2-tier, but it's not quite the same question. So we just have to show you why it's not quite the same person. Right, this is my version of that same story. There are 10 students. 3 are left-handed, 7 are right-handed. Okay, and we are going to create a probability tree for choosing 2 people. So you're picking 2 people at random from this class, and you want to see how the probability tree works. And this particular probability tree is going to have one minor change and one major change. The first one is going to be the first person that I pick. Right. So they could be left-handed, or they could be, oh good, I got it, right-handed. There's 10 students, 3 left and 7 right. The minor change is that in this case, I'm just going to leave them as fractions. The first person that you pick, there's a 3 out of 10 chance that they're left-handed, and isn't there a 7 out of 10 chance that they're right-handed? And the reason I'm going to leave these as fractions rather than turn them into the typical decimal comes next. You're picking 2 people. So in this story, you're now going to have the second person that you pick. The probabilities have changed. The probability that the second person, this second person here, right, is left-handed is not 3/10. Right? This thing is not 3/10. What actually is the chance that for this particular left-handed person, right, the second person I picked on this pathway, what's the probability that they're also left-handed? Clue, haven't we used up one of the left-handed people? That means there's only 9 people to pick from when I get to the second person. Of those 9 people, how many of them are left-handed?
1/3.
Not 3/9, which is 1/3, but haven't we also used up a left-handed person as well as just a general person? So that's 2/9. So this represents a left-handed person's picked, and then from what's left, what's the chance that the next one is a right-handed? Well, there's 9 people, but there's 7 of them that are still right-handed. Now this one was a right-handed person, first pick. What's the chances that the second pick is left-handed? Well, there's 9 people, and there's still 3 left-handed in this world. There's 9 people, but since you've used up one of the right-handed, do you see it's now 6/9? Do you see how those probabilities that I've written here are dependent on which pathway they came from? Right, you're using up a person, and that person might be left or right-handed, and that alters these guys. So when you come to do the end probabilities, right, what's the chances of this happening, or this, or this, or this? Let's see what we get. You multiply these two together, and you will get 6/90. If you multiply these two together, 21/90. These two together, 21/90 again, and these two together, 42/90. And all I'm going to do now is turn these guys into percentages. 6 divided by 90, and that's about 6.7%. 21 out of 90 is about roughly 23.3%. And that makes this the same number, so it's about 23.3%. And the last guy is 42 divided by 90, and that's about 46.7%. Now, from this tree diagram, you can do the A, B, C, D, E, F, G, H, I, J kind of thing. And they want all the answers to be in fractions. So you would be writing 3/10 and 6/90. Well, you wouldn't actually write 6/90, would you? When you simplify that down to 2/30. And then you create a table. Right, from this fella here, I can answer questions like this. What's the probability that you pick the 2 people are both right-handed? Well, the chance, the one of these that represents both of them being right-handed is first person right-handed, second person right-handed. It's this one here. Which is, well, let's get the calculator to simplify it. 42 divided by 90. Math number 1, 7/15. And essentially you can fill in any combination that you would want to do that. So I guess I did end up doing 2 tree diagrams after all. Can you see why I needed to kind of do that? Because it wasn't really the same as the airline one. You know, the numbers were given to you and you're just having to figure out where to fit them. In this one, didn't you have to really think through each of the probability pathways? So it was a little bit different. So a very quick version of a table question. And there isn't any tree diagrams necessary for this one. So let's do an HIV test. Could be any test, but I'm pretending it's an HIV test. So those in the nursing program will probably be aware of kind of where this is coming from. So we're talking about the truth. And the truth is that the person has a disease or that they don't have the disease. Right? So you've got HIV or you don't have HIV. You've got COVID or you don't have COVID, right? You're pregnant or you're not pregnant, right? Whatever it is, you're testing for it. And we'll assume that the world is made up of two groups. You have it or you don't have it, right? So the truth is disease or no disease. Now, what you typically do is you do a test, right? And in that test, they use, very often they use the word, it's a positive test or it's a negative test. You ever had a test and they said you tested positive for COVID, right? Or you tested positive for being pregnant, or you tested positive for having the HIV, right? Negative, the test says you don't have the disease. Positive means you do have the disease. Can it make sense? And in this story, we are testing a new HIV testing, right? We're seeing how good it is, right? And they got this set of data. So for instance, this is 386 people who did not have the disease and the test says negative. So wouldn't that mean the test got it right? Wouldn't this 55 up here be people who had the disease and the test agreed with them, right? The test was positive. What does that 12 there represent? Who are those 12 people here?
False negatives.
Yeah, they call them false negatives. And in English, doesn't that mean that you had the disease, but the test didn't detect it? We don't like tests that do that, but pretty much every test is, I haven't heard of any test in the world that's like 100% correct. Even the COVID testing that you do you know that there's, I'll make up a number because I don't know what it is, but they're 98% effective, right? They do the truth and they tell you what's, you got it, you're not. But there's a 2% missing, right? Sometimes they get it wrong. And so negative test, 12. Now I'll put in the totals because they're nice and they tell me it. So going this way, it's 67 and 433. And the whole thing adds up to a nice round number of 500. We can be asked lots of questions about this. So let's just figure out this one. What proportion of the time was the test wrong? Well, out of the 500 people, how many times did the test get it wrong? Well, it got those 12 wrong, right? Because that represents a false, right? They got it wrong. Isn't that also wrong? And that's a false positive, right? You get the phone call from the doctor and says, we've just tested and it came back positive. Can you come in and we'll do some more tests? Because very often they don't just rely on one test and go with it. And so that counts as a bad thing as well. So essentially, wouldn't this be 20, those two added together, that's 50, what, 59 out of 500. And let's see what that looks like. 59 divided by 500, and that's about 11.8%. Let's find out the proportion that represents that, which is a false negative. A false negative says, the test says you're okay, but you're sick, right? Now there's 500 people, 12 of them fell into that category. And what we have is 12 divided by 500, And the answer is about 2.4%. Okay, what would I be worried about here? I know that's a mistake. Would you agree these are, the test says you've got it, but you don't? But really, what's the damage done? Won't you have a few days of panicking that you might have cancer or you might be pregnant and you didn't want to be or whatever, right? But they'll go in, won't they, and they'll check it and you'll be fine and you won't die of it. Nobody ever dies of a false positive, right? Because you never had the disease, right? So you're not going to die of it, right? Isn't that a much more serious error? We don't like that number to be big. So I guess the judgment call is 2.4% small enough for you to like the test? Well, I guess it depends on what the test is right now. Do you know that the early COVID tests were kind of hit and miss? They weren't actually that accurate. And so you were getting an awful lot of people who thought they were okay and they actually had COVID. Why is that a bad thing? Well, you don't get treated early. You know, getting treated right away is going to improve your chances, isn't it? Then you wait for 2 more days till you get really sick. If it's HIV and you think you're okay, couldn't that be a danger to you and your partner? Because I'm cool, I don't have HIV, I tested, it was fine. And so most people, when they are looking at tests and how effective they are, it's the false negatives that make the difference. That'll worry you, that'll cost money, but it won't kill you. Couldn't that